Okay, so today we're going to talk about water and all of its cool properties, and how it gets its cool properties. If water didn't have all these really cool properties, life on Earth wouldn't exist the way it does, and most of us are pretty happy with that. So this is a really important topic here to cover. Why is water so important? First of all, I think you learned this in like 6th grade or 5th grade. It makes up a lot of our body weight, 70% of it. It's very important as a source of oxygen during photosynthesis. It's a solvent, which means it dissolves lots of stuff. We use it to wash our clothes, right? And that's a very important thing. And us, we wash us because it dissolves the dirt and the stuff off of there. It's a huge factor in the environment. It for tons of reasons. Everybody drinks it. They use it for liquid source. We use it. Well, we don't use it, but the planet uses it to cool and to heat different areas, to transfer heat around the planet. It's just it's got to be the most important molecule we have, and it's definitely essential to life. Everybody should know that. Water is an interesting molecule because it's made out of H2O, right? We know that. It has an oxygen and then 2 hydrogens, and they're kind of bent like this. It's not a straight line. If you see it drawn in a straight line, that's not very accurate. I mean, some people do it just to be really quick, but it's not real accurate. Now, we'll see a picture of this in a minute, but it's polar. It's polar, which means it has a negative kind of end and a positive kind of end. It actually has 2 positive kind of ends. Kind of like a magnet would have, right? Sometimes they have north and south, or like the Earth does. We have poles, so there's different ends that are kind of opposite of each other. Hydrogen bonds are the ones that kind of form and give all the properties to water. So this positive right here is going to love the negative up there on another one, and these water molecules are going to bond together. They can get up to 4 neighboring water molecules, and they can all be sticking together, which is why water is an important thing for us. Here's a better picture than I drew. You can see oxygen with its 8 protons in here is going to really be able to attract a lot of electrons. And if you remember, that was a term we had before. It means it's very electronegative, or has a very high electronegativity. Right? So it's very electronegative. It likes to attract electrons. Well, hydrogen only has 1 proton in there, so it can't really attract a whole lot of electrons, and oxygen doesn't share them very fairly. It shares, but it doesn't share very evenly, and so what ends up happening is we get a little tiny partial positive. That's what this little thing like that is. That means partial, not a whole positive charge like a whole proton, but just kind of a little bit more positive than the say normal. Up here would be a partial negative. And those partial negatives are going to be attracted to the partial positives of another water molecule, and they're going to form hydrogen bonds, and they give water all of its really cool properties that we'll talk about, I think, right now. Let's see. Right now. We'll start with cohesion. Cohesion is something sticking to itself, or more of itself. So when water molecules stick together because of the hydrogen bond, that's called cohesion. They use that in sports a lot. A really cohesive team is one that they all stick together and they fight for each other. So that's what cohesion is. Adhesion is very similar to cohesion, but now it's one thing sticking to a totally different thing. So water sticking to the side of a glass, or to some paper or something like that. It's one thing sticking to another thing. Adhesion. That's tape. We use adhesive tape to stick one thing to another. Right? So that's another way of thinking of that. Here's a good picture of it. You can see adhesion has this paper, which is the F, filter paper, is stuck to the water, and that's called adhesion. When water sticks to water, that's called cohesion. Isn't that a cool picture? Capillary action is the tendency of water to move up little narrow tubes, even against the force of gravity. Everybody knows about gravity, right? Gravity's pulling everything down towards the center of the Earth. Well, if we have this little tube, it's hard to draw a little narrow tube, in some water, right? If there's water right here, and this is full of water, the water will climb this tube. Can't make an arrow very good. The water will climb that tube and go up. Surface tension is on the surface of water. Remember you saw that when you saw the test question that we're going to have on the next test of that bug sitting on there? It's the molecules are attracted to each other in this sideways in this direction, and so things are able to stand on there. Like you can float leaves on there, right? It makes things kind of sit on top of the water, or like that mosquito walking on water. Here's kind of a technical picture, but it really shows it really well. Kind of ignore all the formulas and stuff. The important part is if the water is attracted to this side of this tube, right, and it wants to go up, that is the capillary reaction. When it's attracted to other molecules on the side, that is the surface tension. Surface tension. Okay, see the difference? Good. I know you answered yes, because I just know that. Capillary action works differently with different sized tubes. It works best if you want it really high with a really narrow tube. You can see this is a little skinny tube right here. The fat tube, the water doesn't go as high. There's probably about the same amount of water in there, right? It's just that this is wider here and that's narrower, so it's able to go higher. So the width of the tube kind of affects how high the water goes up in the capillary. Now, another very important thing about water is that it's usually called the universal solvent. Universal solvent, because it dissolves almost everything that it likes. Not everything, but stuff that it likes. It is polar. Remember we said that water is polar, so it likes to dissolve things that like water or are hydrophilic. Means that they're water loving. They interact very easily with water. Those include all things that are polar and all ionic compounds. Remember, ionic compounds are compounds that are formed between ions because of their positive and negative charges. Hydrophobic, though, they don't dissolve and mix so well. Those are like oil. So it's like if we mix oil and water, we don't get this nice, neat solution. We get this nice, big mess. Right? And what happens is between these parts that like water and the water, because water likes water, so it's hydrophilic with itself, these oil kind of make these clusters or clumps of oil in the water. And you see that if you ever do the dishes. You can see all the globs of oil floating across the top. There's 3 states of water. There's gas, liquid, and I don't like this, ice. It's solid, because just because we're talking about water, it still is another molecule, another compound. Solid sounds better, but think of it as ice. Just remember, ice is a solid. When you add heat to things, it causes it to move faster, and it increases something called the kinetic energy, and that's the energy of motion. So that's motion. You have a lot of kinetic energy if you're driving in your car really fast. If you stop, you don't have a lot of kinetic energy. You have a lot of potential energy because as soon as you decide to push on that gas, all of a sudden you're going to start moving. Right? You have the potential to move, but you're not moving, so you don't have any kinetic energy. Now, heat is a measure of all the energy in a substance. All the energy. And temperature is just the average kinetic energy of these particles. So there's a little difference between heat and temperature, and a lot of times we get them confused, but that's okay. For now, just kind of know this right here, and if you get them a little bit confused, that's okay. We kind of think of stuff with a high temperature as being hot, and that makes sense because it means there's been a lot of heat added to it. But we need to start thinking about that a little bit more, especially when you get to chemistry. You need to kind of really know the difference. But right now, just kind of know the difference. Now, when we add heat to water, one of water's really cool things is that it can absorb a lot of heat. A lot of heat. It's one of the things that makes it so nice and cool at the beach when it's super hot out here. It also makes it nice and warm in the beach areas when it's super cold out here, because water is able to store a lot of heat. And it's because of all those hydrogen bonds that are in there. So to make water boil or vaporize, we need to add a lot of energy to it to break all of those bonds, those hydrogen bonds. A calorie, yeah, we should probably learn that. A calorie is just a unit of heat or of energy, right? Another one is joules. Just kind of know those names. I'm never going to ask you to do this conversion. Just know those. What's next? Evaporative cooling. This one's awesome. We've been doing lots of this lately. Everybody's been doing lots of this lately. Humans do it, and it's called sweat. That's sweat, not sweet. When we have water and it starts to heat up, it moves faster, and some of the molecules evaporate and go away. And when they do that, they remove some heat. So if we're really hot and sweaty, we have all this sweat running down us, and we want the water to evaporate and go away, and that's when we cool off, and because it removes heat as it goes, and partly because water can hold so much heat. And that's what this next one, specific heat, kind of says. It's the amount of energy that is required to raise the temperature of water 1 degree. And it takes a lot to do it for water compared to other things. Some other things that heat up super fast. But water is really good at absorbing the heat. And this is the last slide. We're almost done. See how fast his notes were? That was awesome. Hydrogen bonding also affects ice in the way it's formed. Water is actually its most dense at 4 degrees Celsius. Well, it doesn't freeze, so this is most dense, right? Oops, that's an S. It freezes and melts, by the way. Things freeze and melt at the same temperature at 0 degrees Celsius. So this is not frozen yet. 4 degrees Celsius is not frozen. 0 degrees is frozen. When ice is frozen, it'll float on top of the water because the not quite so cold water will sink to the bottom. So that's why ice floats, because this not so cold water sinks down to the bottom. And this is really, really important. I'm trying to find it. This should be on this thing right here. Right here. Lots of lakes, we don't have any around here that do this, but lots of lakes freeze over the winter. Well, here's the lake, like that, right? Here's the water. Right? Usually the whole thing won't freeze. Usually just this top layer will freeze. So down here, all the fishies can swim around and be free. That fish has a bigger tail and it does a body, but who cares? So that's why you'll see guys come out here and do ice fishing. They'll put a hole in there, put their string down, and this fishy will come in and eat the fish, and this guy eat the bait, and this guy gets a fish. If it was the other way around, if water wasn't most dense at 4 degrees Celsius, we would have a lake, and it doesn't matter how big it was or deep it was, as soon as this top layer would freeze, it would sink to the bottom, and then the bottom would be frozen. It would keep going on and on and on until eventually the entire thing was frozen full of ice, and there'd be no life in there at all because it would be all frozen. Except for these frogs. There's those frogs that can freeze and then come back to life. Pretty cool. So that's about it for those. We'll talk about more water stuff later. We're going to lab on it next class, so make sure you've looked at this stuff. And hey, see you in class.